Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is the third video in Lecture 2.1, the Basic Probability and Statistics Review. Here we're going to talk about estimating probability from observations. Now, we did this already with the six-sided die when we were comparing the different methods of estimating probability. Now we're going to move on to continuous random variables. We are on the second topic in our list of topics. So again, we're going to use relative frequency as our tool for estimating probability. So relative frequency is the number of occurrences of the outcome or event of interest divided by the number of independent trials, or the number of times it could have happened. The independent is important. If we see an observation that's the same as or similar to the previous one, because there really hasn't been the opportunity for it to have changed yet, then that doesn't count as a separate observation. Each observation has to be unrelated to and unaffected by the previous observation for us to use it in estimating probability. So relative frequency, how often something happened divided by how often it could have happened. This is a really simple and really effective tool in estimating probability. So essentially we're saying I'm going to estimate the likelihood of something happened by how often it happened. So here's an important idea about relative frequency. This phrase in green is one that we're going to see many times in this lecture. As the number of observations becomes very large, the estimate of probability by relative frequency approaches the true value. Right? So that's great. This is a good estimator. It's what's called a consistent estimator that does better as the sample size is larger. All right, that inspires confidence, but the problem is we usually don't have a very large sample. Right? So this is going to take a little bit of work still. So we're going to walk through the theory of using relative frequency based on an example. Here we have the annual maximum stream flow across 85 years of record. So what we have is the largest flow value in each year in each of the 85 years. These are values that we consider to be independent because each value is from a different year. So we consider the independence assumption to be satisfied here. And this is a continuous random variable. We have stream flow on the vertical axis. In order to get a look at the probability structure of this data set, the first thing I'm going to do is discretize it and develop a histogram. So I'm going to take the flow axis and divide it into bins of 1000 CFS, and then count how many values, how many observations I have in each of those intervals. So between 0 and 1000 CFS, I have 1, 2, 3, 4, 5 values. Between 1000 and 2000 CFS, I have 1, 2, 3, 4, 5, 6, 7, 8 values. I'll continue counting up in each of these other 1000 CFS bins. And the next tab, we have the histogram. So now on the horizontal, we have flow in thousands of CFS. So we've taken off those zeros. And between 0 and 1000 CFS, we have our 5 values. Between 1 and 2000, we have our 8 values. And we have the rest of those intervals counted up as well. So this is a count histogram. If we wanted to see relative frequency, we would divide each of these counts by the 85 member sample size. So what can we tell about our random variable here? Well, we can see that it's more likely to have values in the middle of the range than to have either extreme low or extreme high. It looks fairly symmetrical, not quite symmetrical, but close to symmetrical in that we have about the same number of values above and the same distance above the middle as below the middle, although not quite symmetrical. It does go a bit farther to the high end. So a bit of positive skew jumping ahead. But this gives us an idea of what the probability density function of this variable looks like. So let's formalize the histogram. Okay, a histogram, or class interval analysis, this is placing observations in intervals or bins and calculating the relative frequency in each bin results in a histogram of the observations. And then here's this phrase again, I said would be repeated many times. As the number of observations becomes very large, and therefore the intervals can become very small, the histogram approaches the probability density function for a continuous random variable. This means that the histogram is a very good estimator for the probability density function as the number of observations or as the sample size becomes very large. And when we use it with a smaller sample, we just have to be aware that we have a sample. We hope it is representative of the parent population. This is what it looks like with a very large sample. So this purple histogram is to represent a very large sample from the green distribution. So this green PDF is the parent population distribution, right? So the histogram, the purple histogram, is when it's very large, or from a very large sample, is a good approximation of the parent population PDF. And we can see that the histogram is doing a fairly good job at filling out the areas of the distribution. And if it were a bigger and bigger sample size, it would do a better and better job filling it out. So here we're saying that if we want to approximate the probability of being less than or equal to some value Q, then the sum of the histogram bars, or the number of values less than or equal to Q, is a good approximation for the area under the PDF, which is the probability of being less than or equal to Q. This works also for cumulative. So here's the cumulative histogram of count. Here on the right, we have the cumulative histogram of relative frequency to approximate the cumulative distribution function. As always, the cumulative histogram tops out at 1.0 as the CDF does. So let's look at that for the very large sample. Here we have our cumulative histogram of our very large sample, and seeing that it does a nice job of approximating the CDF of our parent population. So we're saying that the number of values less than or equal to the top of this histogram bin is a good approximation for the probability of being less than that value at the top of the histogram bin. So again, this works very nicely for a large sample, but we don't normally have a very large sample. So this is not necessarily the way we approximate a CDF for a smaller sample. And the problem is that we only have a probability estimate here for the top of each bin. And we could make more bins, but if you've ever made a histogram of a small sample, you see that it becomes less and less informative the more histogram bins you have if they're not filled enough. So we're going to move on to kind of a generalization of the histogram, in which instead of these histogram bins being equal, we're going to change that such that we're going to make a histogram bin that contains exactly one sample value. And in the middle, they're going to be kind of narrow, and out in the edges where there are a few values, they're going to be a bit wider. But we're going to have one histogram bin for every value. Now here, we can't really see easily that this is still a cumulative histogram, because Excel is not cooperative in computing, in showing a column chart with separately spaced bins. So I've drawn in a couple of the histogram bins, but just imagine that this is a cumulative histogram, and each of these points is the top of each histogram bar. Right, so now we've moved from plotting only the edge of every bin to being able to plot every point in our sample and have an estimate of probability for every point in our sample. We are increasing one value, or one unit on the cumulative frequency for each value. So now I'm going to turn this sideways, and I'm going to put streamflow on the vertical axis and cumulative probability on the horizontal. Oops, I skipped an idea. So this is, what would a non-cumulative version of this histogram look like? Well, we had said that each bin was wide enough to contain exactly one value. So the non-cumulative histogram would be all ones. And that would be not interesting at all. So we only use this method to estimate a cumulative distribution function. Okay, now I'm going to switch the axes. I'm going to put streamflow on the vertical and cumulative frequency on the horizontal. And so this is all moved sideways. We still see our histogram bars, but we're going to drop them off pretty soon. Now, though, as you move across the horizontal axis, it's easier to see that with every data point, we are getting one more unit of cumulative frequency, and each data point is plotting at its actual value on the streamflow axis, rather than just which bin it's in. The next thing I'm going to do is take this linear frequency axis along the bottom, and I'm going to turn it into a normal probability axis. Right, so here's a normal probability axis, and it is designed to follow the normal distribution. So I've shown the normal distribution PDF in the background here. And the way this axis works is that I'm going to plot a probability at the location at which this PDF has accumulated that probability. So here on the left, I'm starting with 1% by this point, and I've gotten up to 5% by this point, and 10% by here, and I'm starting to accumulate probability a little bit more quickly as the PDF gets higher. So here I'm at 20%, and then 30, 40, 50%. Now I've reached the middle, and I'm still accumulating probability quickly, so I have 60, 70 to 80%. But as that PDF goes down, I'm accumulating more slowly. 90%, 95, this is stretching out, 98%, 99, 99 and a half. So this is how we make a normal probability axis. And so as probability accumulates more quickly, my points are plotting closer together. And out in the tails where probability was accumulating more slowly, my points are plotted a lot more spread out. An interesting and important feature of the normal probability axis is that data with a normal probability distribution would plot as a straight line. Even when we're not approximating a normal distribution, we tend to use the normal probability axis very frequently. Often we are very interested in how our data compares to normal, even if we don't, even if we're not fitting a normal distribution to it. So let's formalize what we've just done here by plotting all of the data points in this way. Okay, these are called, the estimates of exceedance probability are called plotting positions. So this says we estimate cumulative probabilities of the data points using plotting positions, which is a generalization of the histogram analysis. So first, let's put the histogram analysis. We estimated the cumulative distribution function, or the CDF, by this function. The probability that flow is less than or equal to some value of flow is m over n, which is the number of values less than or equal to q divided by the total number of values. So this is just the relative frequency of values less than or equal to q. And I can estimate this probability for values of q which are the upper edge of a histogram bin. Now, with the plotting positions that we've moved on to, we're considering one observation per interval. And so the estimated probability still looks the same. The probability of our variable q being less than or equal to some value of q is still m over n. And this time we've defined m as the rank. So we've ranked our observations from smallest to largest, and we've assigned a rank of 1 to the smallest value up to capital N, the sample size for the largest value. So if you think about rank, it's really just the number of times that a sample member is less than or equal to the value with that rank. So rank over n, the number of times it's less than or equal to divided by the number of times, is still just a relative frequency. But now we can estimate a probability for each member of the sample, right? So we've now been able to put more definition in the CDF that we're able to estimate. So I'm going to make another change in that I am going to switch from the probability less than to the probability greater than, or the exceedance probability, which we work with more frequently. So I've changed now to the probability of q being greater than some value q. And the way I've done that is I've sorted the data in the opposite direction from largest to smallest and given a rank of 1 to the largest value. So the plot didn't change, and that's because I've reversed the horizontal axis to have 0 on the right and 1 or 100% on the left. We usually put our lower exceedance probabilities to the right. For some reason, we like to have our extremes to the right, the extreme high in this case, which is our interest. A benefit to having exceedance probability on the horizontal is that lets us get a look at the return period in an understandable way across the top. So the return period is the average interval between exceedances of a particular value, and return period is equal to 1 divided by exceedance probability. So 1 divided by 5% or 0.05 is 20. 1 divided by 1% or 0.01 is 100. So the 1% is the 100-year return period, which is the value that's equaled or exceeded on average every 100 years, right? We're careful with that. It's not exactly every 100 years. It's exceeded on average every 100 years. So if we look at all the exceedances, all the intervals between exceedances of a 100-year value, they should average to 100 years. So looking at what we're able to estimate for each of these data points based on the fact that it happened within a sample of 85 years, for the largest event, we're able to say it was equal or exceeded once in 85 years. And so it has a probability about equal to 1 in 85 or 1.2. The second largest event was equaled or exceeded twice in 85 years. So we can assign it a probability about equal to 2 in 85 or 2.4. So why do we have these squiggly equal signs and say about equal to? Well, there is a problem with an estimator that's quite this simple, and that's that the smallest event in this case, or the largest event when we were estimating cumulative probability, that smallest or largest event gets a rank of capital N. And so put into this equation, we have capital N over capital N, or 1. So here we're saying that the probability of being greater than or equal to the smallest value is 100%. And so the probability of being less than that value is 0. And when we ranked in the opposite direction and we were looking at the probability of being less than, we were saying that for the largest event. We were saying the probability of being less than or equal to the largest event is 1, and therefore the probability of being greater than or equal to the largest event is 0. Now, obviously, we don't want to say that. And here we've got it reversed. So we're saying the likelihood of being less than the smallest event is 0. And that's not as bad if we're interested in the upper end, but it still implies a bias in all of our probabilities across the range. And so it is still a poor outcome, and we'd like to improve our probability. So we have other plotting positions. There's about a dozen of them, and they each have different characteristics. Here's an example of 2 of them that we use rather frequently. We have the Weibull plotting position, which just adds 1 to the denominator onto that capital N. We also have the median plotting position, in which we've made an adjustment to the numerator and the denominator. The Weibull plotting position gives a mean estimate of probability, and the median plotting position, not surprisingly, gives a median estimate of probability. So there are also, again, many more plotting positions depending on what your needs are for estimating probability. These are the 2 we use most commonly for estimating a CDF from our sample. So here's that statement again that we've been making with each of our estimators. So we're estimating the CDF from ranked observations versus plotting positions. And we can say as the number of observations becomes very large, the estimated CDF approaches the true CDF for a continuous random variable. So the same statement that this estimator is very good as our sample gets very large, so it is a consistent estimator, which is a very good feature. But again, we have to pay attention to the fact that we do have a smaller sample, and we will learn how we deal with that coming up. I've made one more change to the plot. I've changed the streamflow axis from a linear to a log plot, right? A log axis. So if you recall, one of the features of a log axis is it condenses the values together at the top and it stretches the values below. Often when we plot streamflow data, when we switch to a log axis, the data plots closer to a straight line on this normal probability axis, which means that our log streamflow as a variable is closer to normally distributed than streamflow itself. In this case, the streamflow data set was actually already fairly close to a straight line, or fairly close to normally distributed. If you remember, that first PDF was close to symmetrical. So we did not get a straighter line when we went to the log axis. We've actually got a bit of a preview, but a bit of a negative skew in log space. But this is still the axis that we tend to use. It's got another nice feature in that it never goes below 0. In fact, it never quite reaches 0. So we go from 10,000 to 1,000 to 100. It'll continue on at 10, then 1, then 0.1. And it's nice to have a distribution that never goes below 0 for a variable that cannot go below 0. So that's another feature of the log axis. Right, so here's an estimate of the CDF from our data set. And notice that we really can't go much above the data points that we have, the 1 in 85. We can't go much below the lower. So I'm going to do one more thing here, which is add in this green line. And what's this? This is an analytical probability distribution that I can fit to this data. And an analytical probability distribution allows us to go a little bit further than our data, and extrapolate a little bit, and make a few more assumptions beyond the data set. We don't want to go too far beyond the data set, but we can go some distance beyond. And so that's where we're going to be going in the next section of this lecture. Okay, before we do that, I'm going to talk a little bit about what we've just created here. So the steps that we've just taken have allowed us to estimate the annual maximum flow frequency curve for this location. Right? So we've built what we call a frequency curve, which is really just the probability distribution of annual maximum flow. And a probability distribution is something that lets us estimate the probabilities associated with values of our variable. And they also let us estimate values that are exceeded with certain probability or not exceeded with certain variability. So the curve kind of works in both directions. right? So here I'm going to just pause for a moment on a frequency curve and examine it a little bit just as a reminder. So here we don't have the data anymore. We only have the line, and we've gone from that negatively skewed line of the data set we were working with to one that's a little bit positively skewed or curved upward in log space. We've also got a 90% confidence interval showing here, which we'll talk a little bit more about later. But let's look a bit about what we can say with this probability distribution, with this flow frequency curve. So the first question here is, what is the median of the distribution? If you recall, the median is the value for which half the likelihood is above and half the likelihood is below. So that would be the 50% exceedance. So we come along the bottom to the 50%, up and over, and that's about 3,000. Next question is, what's the 2-year event? So the 2-year event, the exceedance probability is 1 divided by the return period. So 1 divided by 2 is 0.5 or 50%. So this is the same as the 50% exceedance probability. Or you can look at it as the 2-year event is an event that's exceeded on average every 2 years or half the time. So half the values should be above it. And again, that's the median. So now we're coming down from the 2 and over to the same value of 3,000. Next question is, what's the 0.01 exceedance probability event, which is 1% on this axis. So we have the 1 down here, up and over to about 20,000. And finally, we're going to go in the other direction. What's the likelihood of exceeding 10,000 CFS in any given year? Right, so here's our 10,000 CFS over and down to a little bit more than 5%. Right, so that's how we interpret our flow frequency curves. And that is what the steps we went through just estimated for us, was the probability distribution of annual maximum flow. So if you have questions about estimating probability from data, please go over to the discourse site, type in that question, and I'll try to be there and answering it. So that's it for this video. Our next video is going to be review of common probability distributions. I'll see you then.